Alright, so let's focus on the additional exam, 2023 additional exam. So we have this problem right here, and they clearly stated that you're going to use polar coordinates. I don't know why actually the polar coordinates were necessary in this case, because this problem with polar coordinates, it has like some down effects on it, because a lot of a lot of people won't be able to identify that the radius varies in this case, which is why I chose this problem, because it's an interesting problem. And what I would like to show you as well is that like this type of problems that are there in the book. So practice more problems that are in the book. Because right now, if I get the book and I show you what I'm basically saying is that this is this is a similar problem as the one in the exam, just that they changed the function. But look at the bounds; they're basically the same bounds. So practice more problems that are in the book. Yeah. Okay, so now we want to solve this integral. So then we're going to transform to polar coordinates. At first they say sketch, right? Let's try like a rough sketch. But your sketch will be neat, but this is just going to be a rough sketch of that. Y goes from 0 to the square root of 2x minus x squared. But basically we know that the square root of 2x minus x squared, this is basically a circle. Well, a semicircle, okay. Then it's just going to be a quarter of a circle, because like now we see that both bounds of x and y are positive, so that means we'll be dealing with we'll be in the first quadrant. Now x goes from 0 to 2. This bounds here on the last integral right there, on the outer integral, is associated with x, so x goes from 0 to 2. And then from 0 to 2x minus x squared, to the square root of that, that's y. But then notice that 2x minus x squared, you can rewrite this as just half of 2, that's 1, and 1 squared, that's 1. So you're just going to have something like this, plus 2x minus x squared. And if you look here, this is just a perfect square number. This is a perfect square number. So that means that you have 1 minus x minus 1 squared. So the smart thing to do is just rewrite this question right here. The integral from 0 to 2, the integral from 0 to the square root of 1 minus into x minus 1 squared of x dy dx, because why not? So now we can see it's a circle of radius 1 centered at x equals 1. So we have a center there at x equals 1. So if you plug in 1, the y value will technically be 1 as well. So that will be the upper max right there. So now we basically just have something like this. So that's technically that region that we're looking at right here. So now we have a problem. You cannot just say that r goes from 0 to 2, and then theta goes from 0 to pi over 2, because in this case we have a problem, because you can basically tell that you have a full circle, well, a semicircle that lies in the first quadrant, but it doesn't necessarily need to lie in the first quadrant. But now what you can see is that if our angle is 0, remember you have 0 and pi over 2 right there, and then you have pi right there, and then you have 3 pi over 2. So if our angle is 0, our radius is 2. But if our angle is 1, if our angle is here, remember here it's a coordinate 1, 1, where both x and y are the same. Remember, you find the angle theta equals arctan y over x. So if we have 1 and 1, that basically tells you that at pi over 4, the radius is basically root 2, because 1 square plus 1 square is basically 2, and the square root of 2 just would be the length of that radius at that point. So our radius is dependent on theta. In this case, if theta is equals to 0, you have a radius of 2, and if theta equals pi over 4, then you have a radius of root 2. And notice something, when our angle reach pi over 2, we have this dot right here, basically just implying that if theta equals pi over 2, then our radius is technically equals to 0. So in this case, r depends on theta. So now you are forced to integrate with respect to r first. In other cases, in the videos that I've shown, you don't necessarily need to like integrate with respect to r first. You can basically do vice versa. So in this example, you're forced. Okay, so now in this case, we can basically tell that if theta is 0, we have a radius of 2. So basically, we know that r will basically be a. Because at pi over 2 now, we know that pi over 2 is basically going to... what's 0 at pi over 2? It's cos. So we're going to have to correspond that with that. But in this case, you can basically tell that a will be 2 in that case. So a cos theta will be basically what we use for something that varies, for a varying r. So that means this thing, to polar coordinates, we go from 0 to pi over 2. We know that we're in the first quadrant. The whole thing is in the first quadrant. And then we go from 0 to r. R depends on theta. So it's just going to be 2 cos theta. Now x here, remember the polar coordinates, x equals r cos theta. Then dy dx just going to become r dr d theta. So that's the transformation of that. So then you're going to further proceed. Then you have 0 pi over 2 right there. And then you have 0, you have 2 cos theta. And then we're just going to integrate r there. Remember that you're just going to have r squared cos theta right there, dr d theta. Now for the first integral, you know that theta is a constant right there, 0 pi over 2. And then you integrate that, you're just going to have r cubed over 3. Take it from 0 to 2 cos theta. Then you just have cos theta dr right there. I mean d theta. This cos theta. Because you integrated r squared with respect to r. Now you're just going to plug the bounds. Then you have the integral from 0 to pi over 2 off. Plug in 2 cos theta. 2 cubed, that's 8. So you have 8 cos cubed theta over 3. Subtract the lower bound, which is just going to be 0 in this case. So you multiply that with cos theta, d theta. Then from then you're just going to have the integral from 0 to pi over 2 of... notice that if you multiply this one with cos theta, you're going to end up with 8 cos 4, cos raised to 4 of theta over 3 d theta. The wise thing to do is just take the constant outside. I'm just going to take one constant outside. Now the integral from 0 to pi over 2 of 8 cos to the 4th of theta, d theta. Now, in this case, what you basically have to do now is that you have to remember, okay, you have to be strategic in maths. We have a power of 4, but we know something. We know that cos 2 theta, let's say cos 2a, this will be basically be 2 cos square a minus 1. So we know that 2 cos square a, this will be equals to 1 plus cos 2a. That is known. It's what we know. So now we have to express this. We have to find 2 cos square something right here. So in this case, then we have 1/3 on the outside right there. So we have the integral from 0 to pi over 2. And then we have, we're basically going to have like 2 cos square theta square. And what's 2 squared? That's 4. And here we had an 8, so we have a 2 on the outside. So we can rewrite this as something like this. Right. Okay. I hope we're still on the same page. Then we know that we can rewrite 2 cos square theta as 1 plus cos 2 theta. So you have 1 plus cos 2 theta. Then we square that, we have that square right there. So d theta, then we can just expand that. We have 1 over 3, the integral from 0 to pi over 2. So we have 2 into 1 plus 2 cos 2 theta plus cos square 2 theta d theta. Then you have something like that. Right. Okay. So now what we have is like we have 1/3 the integral from 0 to pi over 2 of 2 by this, that's 2 plus 2 by 2, that's going to be 4 cos 2 theta, plus 2 cos squared 2 theta, 2 cos squared 2 theta. But you also have we also have 2 cos square. If you take 2 theta as a and you use this formula again, that it's equals to 1 plus cos 2a, then you can rewrite that integral as the integral from 0 to pi over 2 of 2 plus 4 cos 2 theta plus 1 plus cos 4 theta d theta. That's what we have. Then we have 1 plus 2. That's going to be 3, right? So we have 1 over 3, the integral from 0 to pi over 2 of 3 plus 4 cos 2 theta plus cos 4 theta d theta. Then from then we can just integrate. We have 1/3, and then you integrate with respect to theta, you have 3 theta. You have 3 theta plus the integral of cos 2 theta, that's going to be sine 2 theta over 2. Then, but since because we have this 4 right there, then we're just going to have 2 sine 2 theta right there. Plus the integral of cos 4 theta is just going to be sine 4 theta over 4. Then we take that from 0 to pi over 2. So what we know is that now we have 1/3. Then we have 3 into pi over 2. Then we just plug pi over 2. But if you plug pi over 2 here, you end up having to have pi over 2 by 2. Then we end up with sine pi. And we know that sine pi is just 0. Plug pi over 2 here, we end up with 4 by pi over 2, which is 2 pi. And we know that sine 2 pi is technically 0. And now the lower bound, if you subtract the lower bound, plug 0 is just going to be 0, 0, 0 everywhere. You don't necessarily need to write this, but it's just going to be 0 throughout. So the only thing that matters now is that you have 1/3, and then you end up having to have 3 by pi over 2. And this 3 can cancel that 3. Then you basically just have pi over 2 as the solution to that problem. So that's when you use polar coordinates on this problem. Like I said, I don't know why they wanted polar coordinates on this one, because the issues here, a lot of people wouldn't identify that you're supposed to have 2 cos theta there, because now r varies, r is dependent on theta. Okay, for me personally, I would prefer like the direct integral. Let me show you how you'll directly integrate this one. This problem was easier with direct integrals. So how I'll prefer you to since the instruction was clear, then you'll use polar coordinates, like I did show you how you answer that question. But basically now, let me quickly show you like how this problem was basically easy if you were not using polar coordinates, dy dx. So like I said, it's best to write that integral as something like this: 0 to the square root of 1 minus x minus 1 square. Then you have x dy dx. So because now you only have x and we're integrating with respect to y, then we basically have the integral from 0 to 2 of x, since x is a constant, and the integral dy is just going to be y, and you take that y from 0 to the square root of 1 minus x minus 1 square. So then you basically have this dx. So then you end up having to have the integral from 0 to 2, then you evaluate that integral at y, so you basically end up with something like this: x the square root of 1 minus x minus 1 square dx. So from then, it's a trig substitution. Let x minus 1 equals sine theta. So basically what I'm saying is that x is basically equals to 1 plus sine theta. So if you do that substitution, here you're going to end up with sine square, and 1 minus sine square is going to be cos square, and the square root of cos square is just going to be cos. Then you end up having to have cos theta, and x will basically be 1 plus sine theta. 1 plus sine theta. Cos theta, and then dx will just basically be cos theta d theta. So basically you end up having to have something like this. Then from there you have the integral from 0 to 2 of cos square theta of 1 plus sine theta multiplied by cos square theta d theta. Then you can split the integral. When you split the integral, you have the integral from 0 to 2. Oh, first let me change the bounds first. Forgot to change the bounds. Okay. If x is 0, you have sine theta equals -1. And if you solve for theta there, you end up with minus pi over 2. Arc sine -1 is minus pi over 2. And if x is 2, you end up with 2 minus 1, meaning that sine theta equals to 1. And where's theta equals to 1? Add pi over 2. I mean, where's sine theta equals to 1? Add pi over 2, right? So then you have this integral from minus pi over 2 to pi over 2. To pi over 2. So then you end up having to have the integral from minus pi over 2 to pi over 2 of, you split the integral, you have 1 times cos square theta, that's going to be cos square theta d theta, plus the integral from minus pi over 2 to pi over 2 of sine theta cos square theta. But now, why did I say this was easy using using direct integration without polar? This is an odd function taken from minus a to a. If you remember last year calculus, this integral is basically 0. So this is 0. So the only remain with this one. Cos square theta is an even function. So you can rewrite this as 2, the integral from 0 to pi over 2 of cos square theta d theta. Now notice that you're basically integrating something easy now. Then you can take the 2 back inside there. Then you have 0 to pi over 2, taking the 2 back inside, then you have 2 cos square theta right there. So when we have that, we know that 2 cos square theta is basically just 1 plus cos 2 theta d theta. Then from then it's just a matter of like integration. The integral of that is theta plus sine 2 theta over 2. Then you take it from 0 to pi over 2. Then from then, you plug pi over 2, then you have pi over 2. Plug pi over 2 there. Now you end up with sine pi. We know that sine pi is 0. And then you subtract the lower bound right there. And then when you subtract the lower bound, everything will just be 0. So basically, you just remain with pi over 2, which is the same answer as we got using the polar coordinates right there. This was when we were using polar coordinates, which was the instruction of the question. But here I was just showing you that I personally thought this question would have been better if it was just a direct integral. Well, because some questions, when you look at them, you should basically see the easier way out is this one. But because you were instructed, then you'll use polar coordinates. Okay, thanks for watching, and you can try some polar problems in the other exam papers that are there on Blackboard. Okay.